This is my solution to bonus problem number 2, dynamics. As illustrated here, we have a double inclined plane with a mass sitting on each slope. These two masses are connected together by a string of fixed length which runs over a pulley system which is situated at the apex of our double inclined plane. For this particular problem, we've been given that the masses are able to move freely up and down their respective slopes without friction whilst under the influence of the Earth's gravity. We've also been given the condition that mass number 2 is greater than mass number 1. So the first part of this problem is to express the string tension T as a function of the masses and the angles. And as the two masses are connected together, they will both move at the same time with equal acceleration, and the string tension will also be equal on each side of the pulley. Now, as mass number 1 is greater than mass number 2, we can make an assumption that it will tend to move down the slope of angle beta, which will have our acceleration going around down this way, which in turn will cause mass number 1 to move up the slope towards the pulley. And based on the assumption that mass number 2 is indeed moving down the slope, we can state that the acceleration be positive in that direction of travel, and as both masses are connected by the same string, the acceleration and string tension, once again, for both masses will be equal. So applying Newton's second law, which states that force is equal to mass times acceleration, we can then arrange that equation to solve for our acceleration. So the acceleration is equal to the net of all forces divided by the total mass. And the net force is the sum of all the forces that are aiding in the acceleration minus all the forces that are opposing the acceleration. So therefore, our total forces will be mass 2 multiplied by gravity multiplied by sine beta minus mass number 1 multiplied by gravity multiplied by sine alpha. And therefore, our equation for acceleration can be written as acceleration is equal to the net force divided by mass total, or in other words, mass number 2 multiplied by gravity multiplied by sine beta minus mass number 1 multiplied by gravity multiplied by sine alpha, all over mass 1, mass 2. From there, we can find the tension in the string, and as both masses are once again connected to the same string, T1 is equal to T2. So we can do this one of either way. We can either work it out for force tension number 1 or force tension number 2. I've chosen to work it out for force tension number 2, which is equal to the weight component along the incline in which mass number 2 is going, which is mass 2 multiplied by gravity multiplied by sine beta, plus or minus the force required to accelerate mass number 2, which is mass 2 multiplied by acceleration. Now, if this was positive, mass number 2 would be moving up the incline. However, as mass number 2 is indeed greater than mass number 1, and our assumption to be moving down the incline of our equation holds true, for tension as a function of the masses and the angles is equal to tension number 2 is equal to mass 2 multiplied by gravity multiplied by sine beta minus mass 2 multiplied by acceleration. For the second part of our problem, we are to determine a condition for which the masses are at rest or in uniform motion. In our first diagram, a condition for which the masses would be at rest would be when either mass 2 has reached the bottom of the slope and cannot move any further, or if the string was not long enough to allow this to happen, then the motion would cease when mass number 1 came to rest against the pulley. Another condition that would ensure that the masses are at rest is if there was a sufficient coefficient of friction between the masses and the slope, such that the mass multiplied by the gravity multiplied by the sine was insufficient to overcome this. Another condition which would mean that the masses are at rest is if there was no acceleration. So for mass number 1, where force is equal to mass times acceleration, we rearrange that so we've got acceleration at the front. Now if our acceleration was 0, our force net would be equal to the force of the tension, trying to take mass number 1 up the hill, minus our force bringing it, pulling force, pulling the mass back down the hill, which is mass 1, multiplied by gravity, multiplied by sine alpha, all divided by mass number 1. Now if we bring the mass number 1, multiply it both sides, times it by 0, we have 0 acceleration is equal to mass force tension minus mass number 1 multiplied by gravity multiplied by sine alpha. If we bring our force tension out the front, we have mass number 1 multiplied by gravity multiplied by sine alpha. Similarly for mass number 2, if we set our acceleration to 0, multiply our mass by our 0, we end up with mass 2 multiplied by gravity multiplied by sine beta minus our force tension. Bring our force tension out the front, we have mass 2 multiplied by gravity multiplied by sine beta. And as previously mentioned, our force tension for both sides of the equation, for both sides of our double inclined plane, is equal, which would give us our force tension is equal on both sides. So we can bring our force tension from mass number 1 and from mass number 2 together. With mass number 1 multiplied by gravity multiplied by sine alpha is equal to mass number 2 multiplied by gravity multiplied by sine beta. We can cancel out our gravity from both sides, and that would give us mass number 1 is equal to sine alpha. Mass number 1 multiplied by sine alpha is equal to mass number 2 multiplied by sine beta. And that would give us a condition where our acceleration is 0. However, for this to be able to happen, the forces pulling each mass down the slope are equal. And for this to be able to occur, both those masses and the angles must also be equal. In this case, we haven't been given that information to be able to make that determination. And as far as uniform motion is concerned, that is defined as the motion of an object, or in this case, two objects, in which the object travels in a straight line and its velocity remains constant along that line as it covers equal distance in the equal intervals of time, irrespective of the duration of time. And as our masses are tethered together by a string, any motion experienced by one mass would be experienced uniformly by the other mass. Thank you.